All right, it's 2:30. We're going to go ahead and get started. Welcome to our second week of Advanced Kentucky AP online content review sessions for AP Calculus BC. My name is Aaron Timmons. I'm the Advanced Kentucky Mathematics Content Director. I'm joined by our Access to Algebra Content Manager, Michael Marshall, and today's presenter, Dr. James Bush. He was with us last week. He is back with us for one more week of fun calculus enjoyment. So just a couple housekeeping slides here, and then we'll get started. So we were excited to have so many people join us last week through all of our sessions for all different subject areas. Just a reminder that these sessions are geared for a Kentucky audience. All students and teachers, we want to make available resources for them during this time. However, we welcome all students and teachers from across the world to join us. So during the session, we encourage participation. Please know, though, that any participant causing disruption to the session will be removed. Contact information for all of us can be found here: Twitter handles, Facebook handles. If you think of email questions to email us, feel free to do so. Your microphones will be muted for the entire time. Your videos will be off. Please make sure you leave those videos off. We will be utilizing the chat feature, so make sure you can find that at the lower right corner of your Zoom screen. You can pose questions if you're a teacher or a student. Any questions will be entertained by us. You can pose questions directly to the hosts, or you can pose a question to the entire audience. So please take advantage of that. Please make sure you have visited kyap2020.com. All of our videos will be posted here. This video will be posted by the end of the day. Last week's video is already up, and you can also find information for any other content area that you choose, along with resources to go along with those. So before we begin, I'm going to pause the recording here for about 3 minutes. We'd like you to sign in just so we can get a broader picture of who all is joining us, so that we can make sure we're serving everybody equally. So please take a minute to open up a new browser. Go here. It's a very quick 4-question Google form. It should take you all of 30 seconds, but we'll give you 3 minutes. So we're going to pause recording. Please take some time. Make sure you have today's handouts as well, and then we'll get started. All right, so I'm going to turn things over to Dr. Bush. He can give an introduction as to who he is, remind you what he's done in terms of his past career, his accomplishments, all of that. Again, Michael and I will be monitoring the chat, so please ask away. Any questions, we will make sure we get to Dr. Bush. So without further ado, I'm going to stop sharing my screen. And James, it's all you.
Thank you, thank you. All right, Aaron, thank you, Michael, and welcome once again. James Bush here from Waynesburg University. I am south of Pittsburgh, Pennsylvania. Glad to be coming straight into your rooms there in Kentucky. Teach all manner of mathematics, upper level calculus, upper level statistics. I'm an AP consultant for both AP Stats and AP Calc, but I'm just thrilled to be working with you. Hope you had a great Easter weekend. It was a beautiful weekend here in Pittsburgh. Sun was out, a little cloudy right now. But what I have done this year, now last week we went over methods of integration, but this week is more application driven. But we have to put in those AP integral, BC integrals. And we know what they are, right? The 3 big ones are integration by parts, partial fractions, and dealing with improper integrals of both type. So what I've done is I've folded those into some applications. Some of them are out of the study session, the NIMSY study session notes. Others are kind of twists on well-known problems, and others are out of my sick little twisted head. So let's take a look at my document camera. If the mothership can pull up the document camera. Are they looking at the?
Not yet. I just see your face.
Oh, did the document camera go away? Let's put the document camera back. Okay.
There we go.
Document camera is showing?
We are good to go.
Okay, wonderful.
I see it too.
Here we go. Okay, AP Calculus BC study session. There I am. There's where I'm from, and there's what we're going to do. Okay. My first question is a variation on a problem that I hope you have seen before. I go a little further with this. It may be too long for an actual AP question, but I think the discipline in it is very good. This table, which is no longer to the right, it's down there, gives values of f prime, g, and g prime for selected values of x, namely 1 and 2. Now we're given that the integral from 1 to 2 of f double prime g is twice the definite integral from 1 to 2 of fg double prime. And we are asked to find the integral of fg double prime. Okay, so my first question, and I'm gonna signal to Aaron, this is a multiple choice question. What integration technique comes to mind when you see an exercise like this? All right, here's the question. And feel free to join right in. Very nice. Yeah, we'll give them about 15, 20 seconds there. But absolutely, integration by parts is it. So, all right. Very good. Yay, integration by parts. Classic problem. Let's see the little twist that I've put in. Okay, so I'm going to minimize this. All right, and let's go to the solutions. All right, let's go to the solutions. Yes, integration by parts. Let u be f and let dv be g double prime. Okay, don't forget the dx on the dv. That gives us du and v, and we apply the integration by parts technique. Now, the one thing I want to talk about, and you want to be really, really careful handling combining integration by parts with a definite integral. Now, some of my students, they get a little flustered right here, because at the same time they're evaluating this, but they haven't actually finished the integration. There are a couple of things that I recommend. Okay, one of which is finishing that part. Just finish that out, and then from the table of values, okay, we fill in the numbers. Okay, and that boils down to the 3. And now we're going to tackle this. Right? Well, once again, and this is a little twist on this problem, that this one requires integration by parts twice, not once, but twice. So we'll do it again, this time u being f prime, du being f double prime, dv is g prime, and v is g. So we're going to get the problem right where it should be, right? Right, there's what we had on the previous page, and we're applying integration by parts to this. Once again, we have something that needs to be evaluated, so I thought that I would just work on that and then combine it with the 3. We get negative 19, and that's where we are at this point, okay? Integral of f g double prime is related to the integral of f double prime g. Okay, yep, that's what we have. But now we use the last piece of given information that f double prime g was twice f g double prime. And it's that which we wanted to find. So you can take that, swing it on that side, take the negative 19, put it on that side, and we get a final answer. Whoops, let me pull that up. And we get a final answer of 19. So a classic problem with a little integration by parts twist. We had to do it twice. But yeah, I could easily see something like that on the exam. Very nice. I'm going to be moving pretty efficiently here. Oh, I like this one. I like this one. This. I was inspired by, there's actually a multiple choice question on the series and sequences handout. Okay. But yeah, I took that and turned it into one of these. For what values of r do both of these improper integrals converge? And take a good look. Okay, this one goes from 1 to infinity. So that's what I call an improper integral of the first type. And this one, well, the 0 is the problem child on this one, right? Now, I want to go back to something that I covered last week. It was actually towards the end. And I'm going to very cleverly, or not, all right. Last week, we looked at improper integrals of this form from 1 to infinity of x to the p. which this one certainly looks like that. Now, Aaron, if you could go to question 2A, and my question is, for what values of P does this integral converge, the first one? Okay, for what values of P does that first integral converge?
So we'll just leave this poll running, I guess, through both of your questions, and then we'll display the results.
That sounds good. That sounds good. Okay. Now, I think we might have stumped some folks there. Might be, yeah, what I would like to recommend is, aha, we have a couple of answers. Oh, okay. Somebody answered both of them. All right. Sounds good. This is something you'll want to know. And once again, I can easily see this question being asked. That way they get to assess your knowledge of both types of improper integrals. Okay. All right. Should we take a look at the answer? Yep, here we go. The answer is P greater than 1 for that first type, and P between 0 and 1 for the second type. So I'm putting that in right here. Okay. This will converge for P greater than 1. And this one will converge for P between 0 and 1. And neither of them will converge for P equal to 1, because you'll have the antiderivative will be a log function. I invite you to check that out. But yeah, both types of those improper integrals where a log's involved will diverge. So, okay, so we've got an idea of how to handle this. We'll take this exponent, r plus 5/6, and we'll set it to be greater than 1. And we'll take this exponent, 3r, and we'll set that to be between 0 and 1, right? So there I am setting r plus 5/6 to be greater than 1, and that gives me r greater than 1/6. But the other one, setting 3r to be between 0 and 1, r is less than 1/3. I think we have our answer. I think we have an answer. Both integrals, both improper integrals will converge for r between 1/6 and 1/3. Yeah, it's a great little problem. I rather like that one. All right, on to the next one. I have 10 of them. I hope we have time for them all. We will see. All right. Well, you can't do applications without doing a good old volume of solid. Once again, put in a little twist on this one. All right, we're going to find the volume of the resulting solid when the region bounded by 1 over root, product of 2x minus 1, 3x minus 1, and the x-axis, okay, is rotated around that x-axis. And we're going to consider from the interval 2 to infinity. All right. So if I could go to question number 3, what integration technique or techniques will we use, okay, in this exercise? Yes, somebody's got it. We will need more than, okay, yes, somebody chimed in with integration by parts. Well, we're going to take a look at that one, right? We will need more than one technique. We'll need more than one technique, right? Yeah, a couple of people chiming out, yes. Yep, more than one technique. All right, we'll take a look at it. Of course, look at how many things are getting assessed in this exercise. First off, it was over an unbounded region. That is an error right there, although I think I fixed it in the, just when you think you proofed everything, that should be a 2 to infinity. Yes, the volume is pi times the improper integral from 2 to infinity of the function y of x, and we want it squared. Pi radius squared pi radius squared thickness. That's what I always tell my students for a volume of solid using the disks. This would use the disks. All right. So there it is. Now, happily, my function had a little square root in it, knowing that I'd be squaring it. So the e square and the square root rather annihilate each other. And we're left with this. Okay. So those who identified two techniques, absolutely. We're going to need improper integration. Right? That's a limit. That's a limit. And the technique here is partial fractions. Partial fractions. Now, doesn't matter which one I do first. What you'll see me do right out of the starting gate, I just decided, well, I'll just get that partial fraction decomposition out of the way, which I did. But your next line could be setting it up in terms of the improper integral, setting that upper bound equal to b, and taking the limit as b goes to infinity, which will, well, looks like that comes now. Looks like that's what I did now. So I did the partial fraction decomposition, and then I acted on the improper integral. Could have just as easily reversed those steps. No harm done. All right. Last week also, I talked about a very common error, okay, when doing partial fractions, and the linear factors have a coefficient of something other than 1. Oh, gracious. And again, I love my students, but they fall into the common traps, and you're liable to call this, oh, the antiderivative is 2 over 2x minus 1, 2 log 2x minus 1. No, the 2 is going to serve as your du. U is 2x minus 1. du would be 2 dx. So yeah, that is the log of 2x minus 1, as this one is the log of 2x minus 3. Okay. Looking ahead, if I evaluated at b, okay, and let b go into infinity, I get infinity minus infinity. No, it's going to be a lot easier if I, okay, got to go to my next slide, use the good old laws of logarithms to write this as the log of a quotient. A quotient. Now I'm going to, oh, that shouldn't be there. Come on. I already evaluated. Just when I think I've proofread everything. Okay, but here we have evaluated this at b and evaluated this at 2. Finally, we take the limiting value as b goes to infinity. Okay, 2/3, the ratio of the coefficients there. Pi log 2/3 minus log 3/5. That's a fine answer, But if we wanted to write it as the log of a single rational number, it'd be the log of 10/9. I know that that's a positive quantity, and as a decimal is 0.331. Look at all the good stuff in that problem. We had a volume of solid, we had improper integrals, we had partial fraction, and along the way, a little log workout. Once again, I could easily see something like that occurring. Our job is to try to outguess the good old people at the test development committee. All right, moving on to number 4. Exercise number 4. All right, I'm rather fond of this one. Now, this one is and will be very, very reminiscent of the first exercise we did. Okay, but I have a little given information. I'm giving you the value of an improper integral right there. It's -0.6. I'm also giving you the value of function f at 1. Happens to be -0.14. And this function, whatever it is, has the property that the limiting value as x goes to infinity of x times the function, okay, equals 0. And there are a lot of functions that behave that way. Any exponential decreasing function will behave that way. This actually was motivated by some upper level topics, one of which is in differential equations, Laplace transforms. That's actually what motivated this. And what is it we want to find? We want to find the improper integral, 1 to infinity, of xf prime. So once again, let's go to our question. My question to you is on this one: which integration technique will we need? Three chiming in once again. I'll give it a couple more seconds. Let's give them always 30 seconds. All right.
We got 4 of 9. 4 of 9 in there. We need 5 more.
Okay, great. 5 more. Awesome. Plenty of time. Plenty of time. Yeah, this is fun. I ask a question here, it comes out there. Wonderful. All right. Well, again, this one is very, very similar to that first one. We will need more than one technique, but integration by parts is one of them. Yes. The infinity, yeah, that is an improper integral. I'm sorry, I'll reduce that there. Yeah. So again, right out of the starting gate, or at least my starting gate, I wrote the improper integral as the limit as the upper bound goes to 0, the definite integral from 1 to b. That's your, you see an improper integral, that should be your first move. Absolutely. So what I'm now going to do, I'm going to switch it over to my next page. Okay. And use integration by parts. Yes, very, very similar to the last one. This time x is u, du is dx, dv is f prime, and v is f, right? That way, we get to express the integral as in terms of f and not f prime, right? So that's what we had. And we're going to apply integration by parts right there. Okay, so we've got a lot going on. Now, watch what I do on this one. Watch what I do on this one. Okay, again, we have something to evaluate, and this over here, which we haven't quite finished with, and all this, the limiting value is b goes to infinity. All right. So over here, I start acting on the upper bound and the lower bound. Okay, and we are given we're given the value of f of 1. We're going to see that in a minute, and we're told that this function is such that the limit as x goes to infinity of f of x is 0. Okay. Okay. Right here, I kind of I don't like the phrase distributed the limits. Okay. No, I use the property of limits. Limit is of the sum or difference is the difference or sum of the limits. Okay. Now I'm going to start acting on things. Okay. What I do here is I turn this back into an improper integral. Turn it back into an improper integral because we're given this value and this value, and we're told that f has this property, right? So again, that's what I did there. First I turned it into a improper integral dealing with the limits, and then I turned it back into the improper integral, and the answer is 0.2. And by the way, the function I used for that, f, was roughly e to the negative 2x, roughly. I did it so I got a little more exact numbers there, but that was roughly the function that I used. Yeah. All right. Let's move along to a little differential equations. Melissa has a list of 50 new words that she needs to memorize. Now, the rate at which she can memorize these words is given by this differential equation. This differential equation will this will actually mimic, but it's not exactly, a logistic relation. It's not exactly, but it kind of looks the same. And is the total number of words memorized after t minutes. And we're going to assume that Melissa doesn't know any of the words at time t equals 0. She's given the 50 words and she goes like, what? Wow, I've never heard of these words. And I got to memorize all the words. Okay, so let's evaluate and interpret this definite integral from 0 to 5. Oh, well, for the first time in a while, it's not an improper integral. And so let's take a look, and then we're going to show that the limiting value is 50. Okay, limiting value is 50. All right, so here we go. The let's use this at for part A. The definite integral from 0 to 5 of dn dt is really n of 5 minus n of 0, or we'll use this form. And again, we assume that Melissa didn't know any of those words before embarking on the memorization. This is a straightforward arctan, but you'll want to know this. Oh yeah, you'll want to know this, that the definite integral, well, even an indefinite integral, let's do indefinite, okay, of 1 over a squared plus u squared is 1 over a arctan. We took a look at this last week, okay, u over a plus c. Did do a good job with space management there. That's a good one, and that's what we have there. Very, very straightforward. We've got the constant 500 over pi. Don't forget the coefficient 1 over 5 in front, and arctan of t over 5. All right. We're just going to evaluate at both 5 and at 0. Arctan of 0 is 0. And what we've got is, arctan of 1 is pi over 4. Oh, College Board loves that number. Okay. And it's 25. Now, my question has to do with the interpretation. So I'm going to throw out an interpretation. You tell me whether this is the correct interpretation or the incorrect interpretation. So, yes, there we go. Interpretation. Melissa can memorize 25 words in 5 minutes. Okay. We found n of 5. All right. 5 people chiming in. That's great. That's great. 2 of them say this is a correct statement. 3 say incorrect. So we're kind of split as you can be with 5 respondents. Okay. Anybody else want to give it a try? Well, it is incorrect. Yeah, that is not correct. Now, it depends which 5 minutes. It depends which 5 minutes. We went from 0 to 5. So in the first 5 minutes, or more specifically, I recommend being very specific. From time t equals 0 to t equals 5, Melissa memorized the 25 words. She memorized 25 words. But yeah, in the next 5 minutes, from 5 to 10, yeah, she'll be memorizing less words because her brain is getting full with those 25 words. So yeah, it was an incorrect statement, but yeah, lots to be learned by that. Now let's go on to the next part. All right, next part. Show that the limiting value is 50. Yeah, she's got 50 words to memorize. All right, so this will now be, we want the limiting value of n of t as t goes to infinity. And once again, an improper integral. I had to throw this in somewhere. And once again, in the beginning, we're assuming Melissa didn't know any of the words, right? So I do my usual. I set the upper bound equal to b, take the limiting value as b goes to infinity. And again, this is a very straightforward arctan. Don't forget about the coefficient of the factor 1/5 out here, all right? And there we go. Arctan of 0 is 0. We have the arctan of b over 5 as b goes to infinity. Grab my marker because I showed this last week, but it's something that should be in your little bag of tricks and knowledge of what the arctan function looks like. Okay, that's pi over 2, and this is negative pi over 2. And it's a really good idea to know what arctan looks like. Okay. All right, there's what it looks like. There's what it looks like. So the limiting value as b goes to infinity is pi over 2. So I'm going to stick pi over 2 there, and the 10 pi on the denominator cancels with the 500 pi up in the numerator, and we get 50. 50 is the answer we would expect, right? Yeah, in the long term, Melissa will memorize all 50 words. I should hope so. Melissa's a bright young lady, and given enough time, I can memorize the 50 words. Well, I might need more time than Melissa. So, okay. Let's take a look at exercise 6. Okay. Oh, now this one, I couldn't resist this one. This came straight out of the study packet. It's a great little problem. Kind of a oh, what would you call it? I don't know. It looks like a little bit of a contradiction. G is a function given by g of x is 1 over root x. The problem also defines in general the average value of a function defined on an unbounded interval from a to infinity. It's the limiting value of the definite integral from a to b divided by the length of that interval. So both are both are changing. We're looking at the limit as b goes to infinity. And we're to show that the improper integral is divergent, okay, yet the average value of g on the interval 4 to infinity is finite. All right. Let's take a look at the first solution here. All right. So we want to show that g, the improper integral from 4 to infinity of g, diverges. So we are going to set it up just like an improper integral, right? And, well, now this is not a hard function, right? X to the negative 1/2, antiderivative of that is x to the 1/2 divided by 1/2, evaluated from 4 to b, okay? And there we go. And because the limiting value of the square root of b as b goes to infinity is indeed infinity, not hard to convince you of that, okay? We have here that the improper integral, okay, from 4 to infinity, g of x is divergent, diverges, all right. That one diverges, but what about the average value of g? I like this one. Like anything that makes you stop and go like, wait a minute. Okay. So there I have defined, okay, like the exercise told us how to define the average value over an unbounded interval. And there I have it. Okay, I'm going to put in g. We know what g is. G of x is 1 over root x. Okay. And we already performed that integration. Okay. Let's keep going. All right. This is where I'm going to stop for another question. And my question is this limit right here. What is that limit? What is that limit? Give you some choices there. Is it 0? Is it 1/2? Is it 1? Or b is going to infinity. Could it be infinity? Quick test of your limit skills. Yeah, wait another 30 seconds. All right, well, the race seems to be between 0 and 1/2. Yes, the answer is 0. The limiting value is 0. Lots of ways that you could do that. You could, I mean, in general, before you knew L'Hopital's rule, okay, what you would do is you multiply top and bottom by b, 1 over b. So that one would be 1 over root b over 2 over b, and that would be 1 minus 4 over b, and these all would go to 0, and you'd be left with 0 over 1. Okay, but it is 0. It's 0. Yes, the average value goes to 0. Wow. Okay. G diverges, function g, the improper integral diverges, but the average value converges to 0. Like that one. Like that one. Yep. Number 7. This one also looks like 2 that we saw previous. That's a big hint. But the reason I like it, I recognize that as belonging to some upper level courses. Last week I called reference to mathematical statistics. This improper integral has you finding the average value of what's called an exponential random variable. It also is part of what you would see. I mentioned it before, Laplace transforms. I mean, yeah, it's just a really good problem, really good thing to know. All right. So yeah, number 7. Once again, what integration? I'm going to go back to the basics. What integration technique or techniques will we be using on this one? Okay. Yeah, and again, the 3 major BC integral techniques are integration by parts, partial fractions, and improper integrals. As well as practice with all the rest of them. Okay, great. Good responses. Yeah, some good responses. We will definitely need improper integration. The infinity is a bit of a tip-off. Okay? And we have the product of x and f of x. Okay, so yeah. So there we go. So let's take a look at the answers. Okay. Yes. More than one of these techniques. Yeah, well, we're going to need improper integration and integration by parts. And there's my integration by parts. All right, there we go. Integration by parts. All right. U is x, dv is e to the negative 2x. Take a quick antiderivative and a quick derivative. Right. And we set this up. Wow, integration by parts together with an improper integral. So again, don't forget to set up your improper integral with a limit sign. You will get very little credit otherwise. Oh yes, got to see it. Yeah, what you cannot do is is just keep infinity up there, and then at the very end plug in infinity, because you're treating infinity like a number, and it's more of a concept. But there's my integration by parts right there. UV evaluated from 0 to b, okay, minus the integral of v du. Okay, the du had a negative in it. If you double back, the du had a negative in it, and that's how that became a plus. All right, we take the antiderivative e to the negative 2x again. That gives us another factor of negative 1/2 out there, giving us negative 1/4. And then we just carefully evaluate from 0 to b. There it is at 0, and there it is at b. Okay. We want the limiting value as b goes to infinity. What I did, just do a little rewriting so you can clearly see it. Right? E to the negative 2b, okay, is over here with a positive exponent, down the denominator is a positive exponent. And clearly as b goes to infinity, these, the two denominators, they go to infinity, okay. Now technically a little L'Hopital's rule on that, technically, okay. But both of these go to 0. I mean, another thing to know is that the exponential function goes to infinity far faster, a lot greater than the linear b. Yeah, in the race to infinity, yeah, this denominator is going to get there a lot faster than this denominator. Okay, and hence the ratio goes to 0. The answer is a quarter. The answer is a quarter. As I mentioned, that is an integral that every time I teach calculus-based probability theory, that one comes up, not only once, but several times. Good one to know. And again, what I'm doing here today is trying to fold in more than one technique in a problem. I think that's where they're going to go. I'll be as anxious as you are to see the exam. Nah, you'll be more anxious. But I'm still anxious. All right, let's do another, well, it's not a volume of solid, but it's a volume by cross sections, okay? Region R is the base of a solid whose cross sections perpendicular to the x-axis are squares. Let's find the volume of that solid. And what I want to do on this one, okay, by the way, if you can't see it, the region goes from e to e squared, and the function is y equals the square root of x, x log x. Okay, I just want to pause for a couple of minutes while you might set up this volume problem. Yeah, see if you can set up the volume problem. Yeah, set up the, okay. Okay. Let's see how you did. I like these cross sections, so I don't know. I'm going to use a makeshift prop here. I just have a little sticky note, but of course the cross sections are squares. So you know, well, no, actually I want to take cross sections perpendicular to the x-axis. So the height of my square here is the same as the height of the function. Makeshift prop there. And what you would want to do here, look at this. We'll take a little cross section, of course, right here, and that's the base of the square, and then it goes up. Although you're looking down at it, so you cannot see the depth gesturing to. But yeah, let's take a look. It would be really the function squared. Yep, y of x squared. No pi, because it's not a volume of solid. Okay, not a pi, absolutely. So this is question 8. Let's take a look at this. Right, there's that one. And once again, kind of know what I did there. Okay, square root of x log of x squared. And what technique are we going to use here? We'll go to Aaron here. What technique am I going to use on this one? Okay. Very nice, very nice. All 5 of you said integration by parts. Yay. Yep, classic integration by parts. Yep. Let's take a look, finish this one out. I really want to get to, I've got 10 problems for you, 10 exercises. Okay, so integration by parts, right? This one's a little different. Yeah, when you have x and log of x, usually the x is the u, but not when log of x is involved. No, u is log of x, du is 1 over x dx, dv is the x dx, okay? And v is 1/2 x squared. Yeah, so we apply the integration by parts formula. There we are. Now, I promised that I'd give you a little more advice in terms of evaluating a definite integral where integration by parts is involved. Personally, what I like to do, I like to just find the indefinite integral. And there I am. I'm just finding the indefinite integral. We have uv minus the integral of v du. We have a bunch of x's that cancel, and I've got that one. So that's the indefinite integral. And then I come and I rejoin the larger problem. Okay. Whereas v was expressed in terms of an integral, there is my antiderivative, and I'm just going to evaluate it from e to e squared, and everything works out very, very nicely there. Okay. You'll have access to the solutions to these. So I want to try to get to the last couple. Oh, I like this one. This was of my own design. Kind of like this one. Got to do arc length, right? Arc length is great. Oh, I love arc length questions. Especially, I can do something like this. Here we have a most unusual curve, and it's defined. Y is defined like this. It's an accumulation function. It's the definite integral from 0 to x of this function of t. And yes, that's what this looks like for x going from 0 to pi over 3. That's my function. It's a function of x, and x is up here, the upper bound. Now, I want to find the length of the arc. All right, and we know what that formula is. Arc length, L. It's the definite integral from a to b of the square root of 1 plus dy dx squared dx. So we need the derivative of this function. My question to you, and it's a little bit different this time, okay, a little bit different, okay? To find dy dx, what do I need to apply? Write something a little. Oh, this is why I love doing this in arc length problems. You can make a whole lot of really interesting exercises using what I'm about to show you here. Okay, 2 of you said the fundamental theorem of calculus, and 2 of you said the chain rule. All right, it is the fundamental theorem of calculus on this one, and I'm talking about the one that goes like this: the derivative with respect to x of the definite integral from a to x of little f of t dt is little f of x dx. Yeah, basically it's the derivative of an antiderivative. I'm talking about that one. So that's what makes this one come out just so very nicely, okay? Because there's my derivative. It's root x plus 1 quantity squared cosine squared of x minus 1. I put this into the arc length formula. Now, you know what I did. You know what I did. Okay, I had to stick this minus 1 here so that when you, well, first off, when you square the derivative, it makes that square root go away. Okay, keeping score, that's the 3rd time I've done that this lesson. And then And then of course, adding 1 to it will make that 1 go away. Okay, you still have this square root. Okay, so these ones cancel. Okay, now normally, careful, normally the square root of something squared is the absolute value. Okay, but I'm integrating from 0 to pi over 3, and all of these quantities are positive. So now, all right, I will need, okay, integration by parts on that one. Wow, this one had the fundamental theorem. Well, it had arc length, it had fundamental theorem, and it has integration by parts. Okay, so there I am. I'm applying integration by parts. Once again, I like to find the indefinite integral first, and then go back to the larger problem and put everything in right there and evaluate, and it comes out to be about, as a decimal, 1.273. But I think that I got the major points of that across. Last one. Wow, I'm usually not this good in my own class about gauging the time here. All right, one more time. Here, a differential equation. This is a variation on one that appeared in the study session notes, but I made it a little more challenging. Not that much challenging though. Here's a differential equation, okay? And we have a value of y for a known value of x. My last question is, well, now let me separate the variables first. I want to solve for the differential equation for y. Okay, so separate the variables. All right. Well, the integral on the left side, that's not going to be too much of a problem. But I want to know what you see in the right side integral. Is it an arctan form? Is it an arcsine form? Is it a log form or a power rule form? Yeah, you'll need to recognize your basic forms. Let's take a with this, once we get past this, then it's routine, right? Integrate both sides. Okay. Yeah, this is my students find this form tricky. All right. It is an arcsine form. It's an arcsine form. Yeah. You have to complete the square on this. You have to complete the square on the 6x minus x squared plus 7. Okay. And once you do, you can get it in that form. Now, earlier, I showed you the form for arctangent. Okay, this is a good one to know. Okay, this one is arcsine. I'm sorry, I'm going to call it U. I'm going to call it U. It's the arcsine of U over A, but unlike arctangent, it doesn't have the factor 1 over A outside. It does not. All right, the left side wasn't hard. There we go. There's your form. Let's take our given information. I'm going to buzz through the solution. We have our given information. Once I get to 2 integrals, that's the part that I find my constant. I don't trust my algebra. Well, trust myself to do more algebra. No, I get it right from here. I get the value of C, and then I double back and I put in C. There's C. And then I solve for y right there. Just multiply both sides by -1 and basically flip everything. And then finally, part B has us evaluating y at 3. Threw in that part. Wow, Aaron and Michael, I'm right up to the timeline, but I was able to present what I thought were 10 really, really fun questions. Aaron, I'm going to throw it over to you.
Thanks. Yeah, that was expertly timed. All right. So let me just put up some last minute information here. So again, All of our contact information can be found on the screen. Very special thank you, Dr. Bush. Those of you that are out there that are watching this, if you want solutions, if you are a teacher, feel free to email any of us and we will get you those handouts to you. The sign-in link is right there, along with links to the handouts and our KYAP 2020 website. This recording will be posted there within 24 hours. So most likely this evening it will be up. But if you have any other questions, feel free to reach out to us. Next week, we are going to be joined by Mark Howell, and he will be covering Unit 10 on infinite sequences and series, specifically the topics that we tested on this year's AP exams. So please let anyone interested know they are more than welcome to join us. We are looking forward to having Mark and his expertise. So
very quickly, Aaron, I'm going to put in a plug for that. I'll be watching that one. I love watching Mark Howell speak. Absolutely.
Yeah, definitely. And for those of you that are watching, we have added one more review session in May. Check out our event site for that. We'll have Amy Cash from Bowling Green High School presenting BC exam preparation for the AP exam. It'll be a really good review right before the AP exam the week after. So tune in then as well. But Michael, James, if you all don't have anything else, then we will sign off.
Good luck, everyone. Good luck.
All right, thanks.
Thank you.